Hello, my name is Amber Phelps, and I will be discussing the distribution of ions across the membrane. To understand the distribution of ions across the membrane, we must understand the influence of the sodium-potassium pump. The neuronal membrane potential depends on the ionic concentrations on both sides of the membrane. The important point is that potassium is more concentrated on the inside and sodium is more concentrated on the outside. But how do these concentration gradients arise? Ionic concentration gradients are established by the actions of ion pumps in the neuronal membrane. We'll be focusing on the sodium-potassium pump. The sodium-potassium pump is an enzyme that breaks down ATP in the presence of internal sodium. The chemical energy released by this reaction drives the pump, which exchanges 3 internal sodium for 2 external potassium. The actions of this pump ensure that potassium is concentrated inside the neuron and that sodium is concentrated outside. Notice that the pump pushes these ions across the membrane against their concentration gradient. This work requires the expenditure of metabolic energy. It has been estimated that sodium-potassium pump expends as much as 70% of the total amount of ATP utilized in the brain. Approximate ion concentrations on either side of the neural membrane are represented in this chart. E ion is the membrane potential that would be achieved at body temperature if the membrane were selectively permeable to that ion. The ratios of each ion in this table will become important when discussing the Nernst equation. The equilibrium potential for an ion can be calculated using the Nernst equation. This is where E ion is ionic equilibrium potential, R is a gas constant, T is absolute temperature, Z is charge of the ion, F is Faraday's constant, log equals base 10 logarithm, ion out is ion concentration outside of the cell, and ion I is ion concentration inside of the cell. The Nernst equation can be derived from the basic principles of physical chemistry. Let's see if we can make some sense of this. Equilibrium is the balance of two influences, diffusion, which pushes an ion down its concentration gradient, and electricity, which causes an ion to be attracted to the opposite charges and repelled by like charges. Increasing the thermal energy of each particle increases diffusion and therefore increases the potential difference achieved at equilibrium. Thus, E ion is proportional to T. On the other hand, increasing the electrical charge of each particle decreases the potential difference needed to balance diffusion. Therefore, E ion is inversely proportional to the charge of the ion. We need not worry about R and F in the Nernst equation because they are constants. At body temperature of 37 degrees Celsius, the Nernst equation for the important ions, potassium, sodium, chloride, and calcium, simplifies to these equations. To calculate the equilibrium potential for a certain type of ion at a body temperature, all we need to know is ionic concentrations on either side of the membrane. For instance, the example used earlier, we stipulated that potassium was 20-fold more concentrated inside of the cell. If potassium outside of the cell divided by potassium inside of the cell is 1 divided by 20, and log of 1 divided by 20 is equal to negative 1.3, then the potassium equilibrium is equal to 60 millivolts times negative 1.3, which equals negative 78.06 millivolts for equilibrium potential of potassium. But the resting membrane potential, Vm, is negative 65. How? Now let's get back to understanding why the resting membrane potential total is negative 65. Resting membrane ion permeability to potassium is 40 times greater than sodium. As depicted in this image, you can see that there are several more potassium channels than there are sodium channels. The resting membrane potential can be calculated using the Goldman equation, a mathematical formula that takes into consideration the relative permeability of the membrane to different ions. If the membrane of a real neuron were permeable only to potassium, the resting membrane potential would equal equilibrium of potassium at about negative 80 millivolts, but it does not. The measured resting membrane potential of a typical neuron is about negative 65 millivolts. This discrepancy is explained because real neurons at rest are not exclusively permeable to potassium. There are also some sodium permeability. Stated another way, the relative permeability of a resting neural membrane is quite high to potassium and low to sodium. If the relative permeabilities are known, it is possible to calculate the membrane potential at equilibrium by using the Goldman equation. Thus, for a membrane permeable to only sodium and potassium at 37 degrees Celsius, where Vm is the membrane potential, pK and Pna are the relative permeabilities to potassium, sodium, respectively, in other terms are the same as for the Nernst equation. If the resting membrane ion permeability to potassium is 40 times greater than that of sodium, then solving the Goldman equation using the concentrations provided in the table yields Vm is equal to 60 millivolt log 40 times 5 plus 1 times 150, all divided by 40 times 100 plus 1 times 15, equals 60 millivolts log 350 over 4015 is equal to approximately negative 65 millivolts. Other ion concentrations are negligible for chloride and calcium. So what is the point in understanding the complexity of membrane concentrations? It's to help us further understand action potentials. Unfortunately, in this segment we will be unable to get to action potentials. So what did the student have to say to the young neuron that wanted to be in the PowerPoint presentation? Sorry kid, but you've got potential.